General relativity, step by step. Last time I was considering radial null geodesics, and we've got two families of solutions. We've got a plus and a minus corresponding to these two solutions here that correspond to outward and inward directed light beams. Well, it's all very well to see this analytically, but it's quite another thing to see it graphically. And I've got a thing which I made earlier here, which I can show you like this. This is a diagram which I produced in the R programming language. It took me some considerable time to make it. And what we see here is on the horizontal axis we've got the Schwarzschild radius R. On the vertical axis we've got the Schwarzschild T. And we've got the two families of geodesics, the inward and outward geodesics, which are coloured red and blue respectively. Is that right? Inwards are red, yes, that's right. So we've got these, I guess there's a person stood at Schwarzschild radius 2, and at t equals 0, 1, 2, 3, 4, he sends out, or she sends out maybe, a sequence of pulses of light, which go inwards and outwards, and we can see what happens. Straight away something peculiar happens at r equals 1. I guess you could say it's 2m if you want to use geometrized units, but we can see straight away that this line, well, you can see graphically at least that these lines never seem to cross the horizon of r equals 1 is called the event horizon, for reasons that will become clear later. And so they get closer and closer, but never actually attain it. A couple of other peculiar things happen. I've indicated the light cones by these sort of grey and black figures here, and you can see that they start out at 45 degrees. Far away from the black hole, it's pi by 4 and minus pi by 4, I guess. But as you get closer and closer to the event horizon, you can see how this angle gets smaller and smaller and smaller and smaller. And so inward going light rays, according to Schwarzschild time, never actually make it through the event horizon. What else have we got on this diagram? We've also got the region r is less than 1. I guess r is less than 2m if you want to use those coordinates. And we can see that we've got very qualitatively different behaviour. Now, you'll remember that I said that the radius was the time-like coordinate, because the metric was ds squared equals minus dt squared 1 minus 1 over r plus dr squared of 1 over 1 minus r. And so if r was less than or equal to 1, this term here was your time-like coordinate. The radius was your time-like coordinate. So the time-like coordinate goes inwards like this. And you can see that although the light cones behave a little bit peculiarly outside the event horizon, inside the event horizon you've got this very, very peculiar behaviour. I'll just zoom in a little bit on those, just a minute. We can see that they're actually going on their sides. They're on their sides. And that's signifying the fact, if you look here, this is the time-like direction, and so these lines here are inward, and you can see that even the outward directed light is nevertheless having a smaller and smaller radius as time goes by. So that's why the light cone is switched on, is turned on its side here. And I've indicated that with these arrows here and here and here and here to show that the light is proceeding in that direction and this direction. There are more features as well that you can see on this diagram here. We can see that at r equals 0, this is r equals 0 here, we can see that the light cones themselves, or the light paths themselves, become parallel to one another. Something very, very peculiar indeed is happening at r equals 0. And I'll spend a long time talking about that. But the physical picture I want to take is, if you are sitting here at this particular event here, if you send an inward light beam, it goes there, and an outward light beam goes there. You cannot escape from inside the event horizon. You cannot send a light signal out of your black hole, certainly not a radial one, and of course the non-radial ones are even worse, because both inward and outward directed light beams end up with r decreasing. You cannot send a light signal from inside, from the interior to the outside. It looks like you can't send a message from outside to inside, which seems a bit peculiar because it's got a strong gravitational field. And we'll see later how that's an artifact of the Schwarzschild coordinate system. But for the moment, I just want you to observe this nice picture here. And let's just delete some of these things so we can see it a bit more cleanly. Okay. There's two very peculiar regions here. There's r equals 1 and r equals 0. I'll leave it there. I'll leave it there. Stop.